to those to that YouTube channel in the chat.
Yeah, will do.
So the first session was an introduction to embodied carbon. It's a bit of a primer. We've talked about what embodied carbon is and also the limits on some of the methodologies that we use. And the second session, super interesting, looking at BIM integrations with quite an engaging Q&A session afterwards. So what I'm going to do, I just want to flash up the mini series. So let me share my screen for a moment. Hopefully you can see this. So yeah, so these are the two sessions I mentioned that we've had so far, and yeah, those recordings are available now. Today we've got a session on collaborating with engineers. I'll sort of introduce our speakers in a moment. The next session, which is actually next Wednesday, is available to book now. It's on Eventbrite. That's an in-person event. It's a hybrid in-person event, so you can just join online like this. It'll be, you know, if you want to join online, it'll be no different. But it'll also be an in-person event because it's a tie-up with the RBA Northeast Small Practice Group. So we're going to be hosting that in the amphitheatre at the Farrell Centre. And it's important to note there's a slightly later time because of that. So we're starting at 9:30 and running until 10:30. And we're going to be looking specifically at tools for smaller practices. So tools that practices can use to calculate embodied carbon. So yeah, do have a look on Eventbrite for that. We'll put a link in the chat, and there's a slide at the end where I can show you. So today's session is focused on how design teams can collaborate to drive down embodied carbon. So we've got speakers from the MEP engineering and structural engineering professions, two great speakers, and we've asked them really to talk about what they do, how they think about embodied carbon, what do architects need to know, and how can we work together. They're both going to talk for about 15 to 20 minutes, and then we'll have a Q&A session. So please leave your questions in the chat and we'll pick these up at the end. Our speakers today are Rosie Jones. So if you don't know Rosie, she's an associate at Skelly & Couch, an associate engineer, as leading environmental and MEP practice with an ethos of leading the way to a truly sustainable future. Rosie's a fellow of the IMEC-E and has also over 20 years of experience in designing sustainable buildings by navigating the optimal experience of the building user with minimizing the environmental impact. So Rosie's going to talk on how architects can collaborate with MEP engineers to reduce embodied carbon. And the second speaker today is Craig Higgins. Craig is a structural engineer. He's a structural engineering director at JCC Consulting, based in Newcastle. Craig's a chartered engineer and a fellow of the Institution of Structural Engineers. And Craig's going to talk about embodied carbon in the context of structural design and how engineers and architects can collaborate on with a focus on reducing upfront carbon emissions. And as I mentioned, we'll have Q&A sessions at the end. So I'll stop sharing this and let's go first to Rosie. Rosie, if you want to share your screen and take it away.
Okay. Hi, so thanks Adam for the introduction and thanks all for joining, and I hope I can convey our approach as both as sustainability consultants and as MEP consultants and our approach. And as Adam says, there's a session at the end on questions. If I haven't quite pitched what I'm saying correctly to you, please step in. So what I just wanted to cover with you in my 15 minutes is why, as services engineers, sustainability consultants, we are being asked to do this embodied carbon analysis, why and where our office has been gaining its experience, and how we approach with and align with the design teams so that we're doing something coherent, and the tools that we're using. And then in the latter half, it's more talking about our sensible approach to design, and when we move away from the sort of quantitative analysis and when we're just being sensible. So I hope that sounds like a reasonable skeleton. I'm sure, can I have a nod? Can you all see these slides? Yeah, okay, thank you. So this diagram, I'm sure, is very familiar. This kind of diagram is very familiar to you all. As services engineers, we've been very invested for a long period of time in this operational side of the carbon. But actually, the conversation we're having today and the wider conversation is about the embodied carbon, the carbon that is going into these buildings before it's even built, during the build process, in its lifetime, and then its end of life. And that's where the emphasis has moved towards. And then a wee bit on who's asking for it, and I'm hoping this aligns with what you guys are experiencing. So building regulations aren't yet mandating it. Planning is increasingly asking for it. It's most especially the Greater London Authority. So that's the experiences in our offices. And then a wee bit less, and I've looked at the requirements for the Northeast councils, where this is relevant to you. So Newcastle City Council are explicitly asking for a whole life CO2 equivalent emissions on any major developments. I think it's fair to say, though, that it's not the top of their priority list when they do actually then go to review the planning submission. Sunderland City Council have got words along the same lines in terms of intent, and Northumberland City Council actually barely broach it. So I think the point I'm trying to make is that the Greater London Authority are all over it and insist upon it, and it's a definitive requirement. And then our Northeast councils are moving towards it, but I think are just, it's work in progress, really. Then the other driver seems to be there's some procurement standards that are mandating carbon reporting, which I've had personally less experience of. And then sometimes we get visionary clients that are requesting it, sometimes as part of their accountability, sometimes as part of the BREEAM assessments. And then in exceedingly good news, the building award bodies are asking for it. Things like the RIBA awards, the Chartered Institute of Building Services Engineers and the Institute of Structural Engineers are beginning to ask for these embodied and whole life carbon assessments for their applications, which is definitely a good thing. And in terms of our experience, I should say, have I been clear that we have a role as sustainability consultants, which effectively means that we're compiling these reports, which is why I've got a good idea of what the whole, like the wider scheme is. But also our bread and butter is services, MEP consultants, is that we're just feeding into that services portion of the analysis. And these are a few examples of the jobs that we've been asked to do these embodied carbon assessments on. We've got Emmanuel College, Cambridge, we've got Mansfield College in Oxford, we've got Christ College in Cambridge, and then some more local ones. We were asked to do an assessment for a project in the Ousbourne Valley that we've done with Will Mawson, and also this new sixth form and higher education centre that we've got in Sunderland were also asked to do embodied carbon. And the most successful ones are the ones where it's embedded in the planning application, which is when you're actually having to do the analysis with options at stage 3, with a final design at stage 4, and then again is what's actually been built. And in those cases, it's had like the analysis has had sort of a meaningful input because it's helping you make decisions rather than sometimes, admittedly, for the award applications, we're just asked to do an analysis of the as-built building, which gives us a benchmark, but it hasn't really given us some kind of optioneering. That makes sense. So ultimately, it's the planning driver that is causing us to make the design team to consider embodied carbon approach from the beginning. I was sort of hoping if anybody, some nods to see if that's that's their experience too. And then I move on to how we align with the wider design team. And I'm sure you're all aware of there's many conversations have gone on about how we distill, how we do the calculation method and how we set our targets. And where we are currently, fortunately, is that we've now all agreed as an industry that effectively it's these two documents where the Royal Institute of Chartered Surveyors have set out the methodology, and all of these bodies have come together to set the targets in the UK zero carbon building standards. So that's our starting point. And then the analysis is done a wee bit like a QS does an analysis when the building projects first start. We get a carbon budget on a meter squared basis, which we take from the targets set out in the UK net zero building standards, based on subsector, and also based on the year that the project's going to be built. I'm hoping this is quite familiar to you. And then in terms of breaking it down into sector, it was actually the LETI document that we use as the base point. They've broken it down by building type, and then we use that to effectively give each consultant or each sector a carbon budget to work to. And then again, like the QS approach, once we've done the meter squared basis, we then break it down a bit more elementally. This is the process that's set out by the Chartered Institute of Building Surveyors. And then this diagram, this chart, is from a recent project that we've actually done the whole analysis upon, the whole embodied carbon analysis. And what I want to demonstrate from it is that we've used these modules that RICS have set us up, and then we've converted those modules into the building categories. And then there's a bit of a black box database that's going on, which converts you from these categories, from these modules into the categories. And then this is the demonstration of the services as inputting maybe 10 to 15% of the overall upfront embodied carbon. And it goes a little way to explain why the services are a wee bit behind structures. If Craig's still on here, in the fact that the structures are the big hitters. They're these purple, orange and green sectors, which is it's making up more like sort of 60-70% of that embodied carbon. Yeah, it's just hammering that point really, that we're a bit slow on the uptake, but we're a smaller portion, and actually what's in our portion is really quite complicated. And what makes that a bit, again, to emphasize that this diagram here is what goes into this is the whole life charts, where the diagram you saw previously with that 10% is this finger. But then when you're actually considering the whole life carbon of the building, the fact that these services are being changed 2 or 3 times, even 4 times in the lifetime of the building, rather than the structure, which is not changing within the lifetime of the building, that's where the services are beginning to have a 20-30% impact. And this is what we're catching up to. So we're quite proficient again. We're exceedingly proficient in the operational carbon aspect. We're getting more proficient in the upfront embodied carbon, and we're getting a grips on the whole life carbon. And the tools that we're using are, the software is the one-click LCA. And this is the software that we've all, basically the industry has agreed to use, and it contains that sort of black box database that is taking us between the modules and the categories. And the methodology that we're using in order to generate that database is this, the agreed tool is this SIBSI TM65 methodology, which is a specific tool that for MEP systems, like, so it's been built up by the Chartered Institute of Building Services Engineers. The goal is that it's a generic database of all of the engineering systems, but it's work in progress, and it's like a pathway, and it's a verification process. So it's a bit collaborative between like the consultants who are working out what these buildings are needed, what the suppliers and the manufacturers are able to provide to fulfill those loads, and then how we can compare those different suppliers. And then we can either, at the moment, we're sort of slightly blindly plugging that information that the suppliers are giving us into one-click analysis because that's all that we're able to do. But actually, we're also giving that information to CIBSE, who are verifying that information and consolidating it against other suppliers' information. And then the goal is effectively that you don't ask for a CIBSE or a Clivet heat pump, that you're asking for a, like, what's the embodied carbon of a 500 kilowatt heat pump. So we're on the way. We're just not there yet. Yeah, so just to cover, like, just to summarize those slides we've already been through, is that effectively our approach is that we get an upfront budget, and our limits are set from the UK building standard. The services approach is a wee bit behind the structures, in that you saw that actually we're at more like 10% of the upfront embodied carbon. And then the reason that the industry is a bit slower about it is that 10% is then made up of lots of many intricate systems, all of our drainage, heating, lighting, water, comms. And so each of those independent systems are made up of multiple components. So whoever's writing that database has basically got quite a big headache. So that's what we're catching up with. And like we've demonstrated that the focus is actually on the M&E systems over the lifetime of the building, so minimizing how many times you need to change those services. And then, Adam, I'm sticking within my allocated time slot.
You've got loads of time, Rosie, don't worry.
Okay, good. So, I mean, I think what I've talked about up till now has been the very quantitative approach in terms of how we distill down, how we put that carbon into numbers. Whereas now I want to just talk about how we approach it in a more sensible manner. So even buildings that we're not doing the embodied carbon assessment upon, how we ensure that those buildings have, like, sort of the minimum amount of carbon, the optimum amount of carbon, like just the embodied carbon that it needs. And this is not dissimilar to the way we address operational carbon too. And I think, the overriding message is effectively, if you're spending less money, you're probably buying less carbon too. So that's a bit of a simplistic approach to it. But if we break it down a wee bit more, what we're looking to do is we can design the embodied carbon out using like natural and passive systems. So this is a diagram of the environmental strategy of the Hixa building that we did with Will's office, Mawson Kerr's office. We're looking to optimize natural light with these roof lights. We're looking to optimize natural ventilation pathways so that air has got reach through buildings, and we're not having to introduce carbon-heavy, cost-heavy mechanical ventilation systems. So that's effectively step one. And then this is moving from the environmental strategy drawings to what's actually been built. And all the feedback is it's working very successfully. And then a big one for us is, can we just limit the length of the distribution routes? Can we just look at being really sensible about where we put the plant rooms? I mean, like I say, step one is basically try and get rid of as many of the complex systems as we can. Step two is, like, let's be really sensible about where to put plant rooms so that we're minimizing effectively the spider's legs of pipes and cables that emanate from those hubs. And then the next few diagrams are sort of my office's BIM team got quite involved, quite excited about showing us to demonstrate the extent of the building services within the building. So it gives us the scope for what we can minimize. I think this demonstrates quite well the extent of the building services. This one is like all of these pink and blue are ventilation systems. Let's try and get rid of those by using natural ventilation systems. And then these pipes, they're always on flow and returns. So if you can give it a central hub, then we're reducing those pipework runs. This is another demonstration of all the pipework coming out of the plant room, remembering that it's all flow and all return. So just keep reducing those legs. And then the BIM department kept giving me more diagrams. So again, this is the extent of the services distinct from the other building elements. So yes, I think it's just really just to show the extent of the building services systems and the impact that we can have. And then we move on to maybe we should be looking at the materials that we're using for those pipework systems. And you know, plastic, excellent, low embodied carbon, but we're not that sure of its environmental impact. We're not that sure of how it's going to be recycled. We're not quite sure of the post-process. Whereas copper, the very traditional material, it's got the highest embodied carbon, but it can be recycled. It can even be reused. So again, it's not one answer fits all. And I think in fairness, pipe material is probably dominated by other factors rather than its embodied carbon, but it's on the list effectively. And then again, you know, we can look at taking centralized hot water we can look at local hot water rather than centralized hot water, so that we're not having to take those spider legs of pipe works. And then I'm sure you hear your services engineer telling you a lot about reducing loads on your building. So as soon as you start reducing your heat loads, lots of insulation, good air tightness, good thermal bridging, then you're actually reducing the peak load of that building and thus reducing the plant that you need to install. So again, just this overriding, just get rid of your systems, reduce the peak load of those systems, share those systems, and you've already gone a long way to designing the carbon out. It's probably a good place to stop, Adam, and to take any questions later.
Yeah, that sounds great, Rosie. I mean, I've got so many questions to not because you've left me hanging on certain things, but you've just made me think, God, I've never thought of that. So I've got so many things to add into the chat at the end, but I'll leave it for the moment, and we'll let Craig have a shot at it first. Thank you, Rosie. Craig, if you want to share your screen.
Certainly will. You all see that there now?
Yeah, we can see that. Thanks.
So I'm going to basically start off on the basis that everyone is aware of embodied carbon. Everyone is aware of material choices around prioritizing timber, renewable resources, that sort of thing. And I'm really going to focus a lot around what Rosie said on slide 17, which is just about trying to think about the things which are going into the building before developing the plan of the building. And also when she mentioned thinking about the embodied carbon at early stages, so trying to get it done at RIBA 2, RIBA 3, is also where you're going to be more successful. So when you develop a plan with the structure in mind, with the services in mind, so you can try and have efficient structures and services before going too far and boxing yourself in. So I've got this first slide here, which is, there's not much information on there, but it was really just to give a bit of a thought in terms of, you've got 7 different beams there, and you can see the plan depth of each one of those beams. And then when we come to the end of the presentation, I'm going to show you essentially the weight of each of those beams, and then how far each of those beams would span under a 10 kilonewton a meter load. And that's really just to stem again the thought of how you can collaborate with engineers in developing your layout, your arrangement, your plan, your sections, your elevations, and how a lot of the decisions about the embodied carbon and the structure happens before structural engineers involved. So one of the main things I think that often gets missed, which is best developed early doors within a scheme, is lateral stability. So obviously I think everyone understands that buildings have beams, columns, or they have walls. they have floor joists, you've got slabs. But sometimes one of the big dictating factors in the ability of a structure to be low value in terms of its carbon, its embodied carbon. And the thing with structures as well is carbon has a direct cost. So whilst Rosie mentioned if you have less carbon, you have less expense with M&E, your building services are a bit more complicated, whereas building structures aren't that complicated when you're measuring carbon. It's the more material you have, the more carbon you have. And you'll often get people who talk about low carbon steel and low carbon concrete, but those things aren't necessarily real. So low carbon concrete, where you have additives, isn't really sustainable because those additives are actually a scarce resource in themselves. And then electric arc furnace steel, if you specify that, you've not really saved any carbon because that steel would have been used elsewhere. It's often going to be imported rather than produced in the UK. So if everyone in the world had electric arc furnace steel and specified it, you're not actually making any difference on global emissions. It might change your project locally, but globally it doesn't make any difference. So the only way you can really truly reduce embodied carbon within a structure is to use less material, and using less material is less expensive, which is probably, as Rosie pointed out, why you end up in a scenario where structures in particular has always had a bit more of a focus on reducing carbon, and different engineers approach things in different ways. And sometimes you get some people with a more efficient design, a less efficient design, but overall there's a focus on carbon because there's a focus on cost. And for the last 20, 30 years, it's never been said, oh, we need to reduce the embodied carbon in this project. But you'll have all worked on a project where someone said, we need to reduce the price of this concrete. We need to reduce the price of this steel frame. And what they're saying without saying it is, we need to reduce the embodied carbon. So yeah, in terms of stability systems, so buildings need to not fall over. That's a pretty important fundamental aspect of it. So in order for them to not fall over, they have to have a lateral stability system. So what that means is either braced or moment frames, or for traditional structures such as timber frame or masonry buildings, it's cellular. So you're using your return walls to resist the wind load from the opposite direction. I'm not going to dig too much into the ins and outs of it, but essentially the wider you can make something, the less material you need to resist those forces. So if you can imagine, if you were to stand up straight and someone pushes you, you'll resist more force if your feet are standing wider. So you've got the exact same amount of resistance to that force in your individual bits. So your legs don't get any stronger, but by putting them wider, you become stronger. So if you're going to make sure you allow enough room on plan to provide a stability system which can be wider, then the material put into it will be less because it needs less resistance to force. And if you can allow bracing, so bracing is essentially allowing members to stretch, and steel is a material which can resist tension better than anything else. So diagonal bracing, if you're always thinking about where can we position bracing, you will end up with a more efficient structure, you will end up with less embodied carbon. I've just included here a slide from something where it's a presentation we've done for structural engineering students, just talking about good and bad practice. So whilst we're talking about bracing and making sure that you allow appropriate plan depth for it and places to put it, it's also trying to make sure you've got a symmetrical layout in a building. So if you have a building where you've got one wall fully glazed, an elevation fully glazed, you will end up with a less efficient structure and you'll end up with more embodied carbon. And that isn't an influence of the engineering, that's an influence of the decision made to not have a wall there or not have a feature brace or something like that. So again, I'm not really drilling into too much in terms of what the bracing's doing or why it's doing, but you should always be thinking about when you're producing a plan, have I got appropriate places on this plan to provide a stability system for the building to not fall over. I'll just skip through this slide. So this is essentially just showing you how a brace bay would be and skip on the next one. So the next one, which often adds a lot of embodied carbon into a structure, is transfer structures. So again, when we were discussing how you can collaborate with engineers to make sure that you end up in a scenario where you can reduce the embodied carbon in a building, it's the most simplest way is making sure that your plan stacks up. So if you've got different plans from floor to floor, and this is whether you've got timber frame structure, whether you've got a masonry structure, whether you've got concrete structure, you've got steel structure, you will add embodied carbon by not having continuity of structure. So when you're developing a layout, if your priority is embodied carbon and your priority isn't something else, then you're best off asking for that layout to be developed around a structure first. So say to someone, this is the plan size of the building. Can you give me an outline structure? And we'll then develop a plan around that structure. And that would be the lowest embodied carbon you could get. This is just, again, really explain what a transfer structure is. I'm not going to, again, drill too much into it, but just demonstrating, if you can see on that picture there, the difference in size between on the green side there, just a standard steel beam, and then how deep a transfer beam gets, because on plan, there's a reason why we've had to step columns. It just adds a significant amount of additional material in there. And then for the final slide, and then I'll just talk through a little bit. So that there, I don't know if anyone had a bit of a guess in terms of those first 7 sections, but you can see there that your instinct would be, as the beam gets shallower, it will get lighter and it will get less strong. But if you look, the difference between beam 1 and beam 2 there is you've got additional mass in beam 2, and it won't span as far as beam 1. So that is mostly dictated by a lot of construction in the UK for structures isn't actually dictated about when it will fail. It's dictated about when it'll deflect too much. So it's normally deflections that are governing. Deflections meaning how much a beam will move vertically over a given span, or how much a slab will move vertically over a given span. And you have to limit those deflections so that it doesn't impact the finishes, doesn't impact the ceilings, doesn't impact the building services. And this sketch really is showing you another thing, which is what Rosie was saying, is just integrating services and structure into a building at early doors of saying, well, actually, do I have an appropriate floor-to-floor height? In order to be, because if someone's set a floor-to-floor height and put in a planning application and gain planning for a building before they've got a services strategy, before they've got a structural strategy, then the reality of it is your building will probably have already failed from an embodied carbon point of view, because, as Rosie pointed out, between 50 to 60% of that embodied carbon is going to be structure. And yes, there's no way you can not have a structure, but the decisions you've made might make the difference between your steel frame or your concrete frame being efficient or inefficient. And you might have essentially set up an impossible task. And that's pretty much ready for questions.
There's a lot to think about there. Thanks, Craig. So, I mean, as I was listening to both of those presentations, it seems to me that there's 2 key themes that came out of that. The first one, which actually is not something that we necessarily think about, but less is more. You know, the less stuff that we can put into a building is critical, and I think architects working with engineers to facilitate that has got to be good, not only for the fact that it's going to save the client money. And that's something that we have, certainly in the sort of sustainability forum, we've been going now for about sort of 5 or 6 years, but we've banged on about this time and time again, specifically in relation to things like passive house design. That little things like designing out unnecessary corners and buildings, can have a big impact in, operational carbon and also embodied carbon. So that's the first one. And the second point, which I thought was really interesting, was that both you, Rosie and Craig, have stressed the key importance of having really early engagement from engineers. I mean, so many times, I see this where an architect, and we're all guilty of this. The client comes along, gets the architect to design a building, take it to planning, and then you involve the engineers, and actually it's too late. There are some key decisions that can really help with embodied carbon, as well as cost saving and value engineering, that can be made, right at the outset. So yeah, really fascinating. But Rosie, I wanted to start with a question for you. I was intrigued by this carbon budget that you talked about almost, as I understood it, you were sort of suggesting that you, at a very early stage in the design, you could almost set a budget and give each sort of team member an amount of carbon that they can expend. Could you talk a bit more about that process and about have you used that in practice, and how has it worked, and have people engaged with that? And because it seems like a perfectly logical approach.
Yeah. Most of the schemes that we do where we are acting as the sustainability consultant, so writing the reports, doing the whole analysis, is that, I hope I conveyed this effectively. You need a benchmark at the very beginning, and certainly when you're doing it for the planning applications in London, Oxford, Cambridge, the planning condition is that you have to comply with the limits set out in the UK zero carbon building standard. So if I reshare. So the wording on the condition effectively says that you need to comply with the limits set out in this carbon standard. And then this carbon standard tells you, look, if you've got let's say a higher education building and it's going to start being built in 2028, then you know that your carbon budget is 545 across all sectors. And then, which is a great number in terms of planning, but then effectively as consultants, which have all of these components, like we don't really know what then our allowance is. So yes, then we're using this LETI base point that splits up into these sectors, and then we all get a portion, and then like the structural engineer goes away with his or her 55% budget, which if that was 55% of whatever the 550, so they've got like 302 kilograms of carbon per meter squared to work with, and then they go through this. Actually, quite often the structural engineer does it first. They work through their structural options and it gives us their actual quantitative number, and then often that will lead to us readjusting for everyone else, readjusting for the M&E, readjusting for the internal finishes, and it fundamentally sets the tone, it sets the base point, and it sets us actually starting to do optioneering exercises. It's sort of giving us all a really thorough understanding of the impacts on that pre-planning choices on the structure, pre-planning choices on the services. Effectively it leads to the optioneering like period of design.
And it gives people a framework to work with, which I think is really important. In a sense, as design teams, we're reasonably comfortable with working to a construction budget in terms of cost. But so it's something we can all consider. So yeah, that's really interesting. And I think I'm fascinated that you've shared that extra. I've just shared a link for the Net Zero Building Carbon Standards in the chat. One of the things that I think is really useful about that document, and as Rosie has explained, if you don't know this, as Rosie has explained, it's essentially a government document that has a lot of buy-in from the industry. But the annexes do have lots of building types, and they show the pathway for getting to zero carbon by 2050, and it's not sort of zero carbon, because a building can never be zero carbon, but it shows the pathway to meeting what the UK is aiming for. The other useful case for that document, and I'm just going to mention this now because I think it's going to be super useful for people on the call. If you as Rosie's mentioned, if you're doing an RIBA awards entry and you're generating what you think is an appropriate, or you're generating a figure for an embodied carbon, you can actually use that document to sort of understand where you fit into that sort of pathway. A lot of embodied carbon tools will kick out a number which is maybe 500 kilograms per meter squared, but it's understanding what that number means. And so the net zero carbon building standard is a great reference to be able to refer to.
It's really
thanks,
hard,
Rosie.
Adam.
So
I should say those targets are really hard too.
yeah,
It's not just a tick box exercise. It's
yeah,
and it's hard now, and it's getting harder, and that's what we're facing.
yeah. It's that constant ratcheting up of what the target that we're aiming for. Craig, there's a question here in the chat from Will saying we're seeing a lot of cost and carbon in the ground. Any top tips on reducing significant concrete infill? Weight of the building is often mentioned.
Yeah, so the carbon in the ground, carbon in concrete is something which will exist and you can't really get rid of. One of the things the I-struct is a little bit ahead of riba on is in terms of not just measuring carbon, but trying to reduce the embodied carbon. So one of the first things they do is as a structural engineer, we should always challenge at the start of the brief is, does this building need to be built? Like, does it genuinely need to be built? Is there another building that can perform the same function that can be refurbished? Because ultimately, if you've got an existing building, then you've got something that you've got your embodied carbon there already. Realistically, and in the reality of life, that isn't always going to happen because people can't just say, oh, well, I'm not going to build on my site, because building is ultimately a commercial venture. So people are either developing for money or they're building for money. I think what we can do is say, well, concrete foundations in the ground can last forever. They can last forever. So when you design a building, it's going back before about thinking about the plan, accept that that carbon's going to go in, but is there a way that you can ensure that building will have an appropriate lifespan, but then once its lifespan's over, that it can be reused for something else? So that's, again, just thinking about plans. So if you set out a design which will be one thing and is very, very good at being one thing, but can't be anything other than that, then again, you've probably missed the point of thinking about embodied carbon, because you've got a building which in 40 years' time isn't going to be fit for purpose anymore and it'll be taken down. Like, if you think about the number of office buildings you'll see from the 80s or 90s or university buildings, where they're being taken down and rebuilt because someone somewhere looks at it and says, oh, we can't justify keeping it for X or Y reasons. And I think as a creative profession, there should be more thought about saying, well, how can I have creativity within, instead of just a blank page, within a set of parameters? So if you could think about it and say, well, actually, if we have a 6x6 grid, or even take a squared paper and put 3x3 grid on it, and make sure every single item of structure we put fits in that 3x3 grid. So I'm either going to have 6 meter base, 3 meter base, 9 meter base, and the foundations only go in those positions, then you should have a building that can be reused. So even if you get to a point where the entire building fabric's finished, and let's say for some reason building heights need to change, or there's any multitude of reasons, you could always reuse those foundations. So someone in 150 years' time can reuse those foundations. So then, instead of focusing on saying, well, actually, we've got embodied carbon within the foundation, if you can use it in an appropriate way, it's not waste. It's only waste if you design a building that'll be wasteful. And I know that's not necessary. There's loads of ways where people can distract themselves from it and say, well, I'm going to try and use a different type of foundation. I'm going to try and use a different type of concrete. But those things are really tinkering with what the real problem is. And the real problem is we waste buildings. And we waste buildings because there's no foresight and flexibility of use.
And the the industry standard idea that a building lasts 60 years is nonsense, isn't it? Really,
Yeah. About 20 years ago, when I did my review, so when you apply to be a structural engineer, it's very similar to applying to be an architect or a mechanical engineer. You'll do a portfolio of work, you do a review, you do an exam. The iStruct is a bit different as much as you do an exam. And sustainability was one of the items that was measured. And I put in my portfolio, we'd been doing a lot of jobs where we were reusing existing buildings. And I put in my portfolio about the way I demonstrated sustainable design was trying to adopt the reuse of buildings and promote repair, justifying load capacity. And I remember at the time being told, well, that's not really sustainability, is it? You need to be doing things like identifying how you perform against the BREEAM and the Code for Sustainable Homes. And you sort of think, oh, that's ludicrous. And then maybe 5 years after that, the iStruct had totally changed its tune and say, well, actually, sustainability is embodied carbon. Then probably 10 years later, you had the RIBA Architects Declare thing. And so there's industry tools to measure things. There's a lot of tinkering around the sites, but the reality of it is any single person on this call, the way you can influence your impact on the world is just good design. And by good design, I don't mean having something which is really brilliant now. It needs to last. And then when it doesn't last, it needs to either be, you can take it down. So there's a lot of emphasis on the number of jobs you'll work on where you'll not know it, but the composite construction. So you'll tie a steel beam to a concrete slab to reduce the weight of the steel beam. And that is brilliant if that structure is going to remain forever. You've reduced the initial embodied carbon that you've used, but you then can't reuse that steel beam because you can't deconstruct it in the future. Whereas if you didn't have a composite member and it was a bit deeper, then as soon as that building is no longer fit for reuse and you take the slab out, you can have a precast unit which you could remove. You can take the beam out. At that point, that beam just needs to be put through a sandblaster, and repainted and reused. And the same thing again, if you have standard grids, 6, 9, like multiples of something sensible, then when that beam comes to get reused, it doesn't need to be cut up. It literally can just be reused in a different building for a different purpose in 100 years' time.
Absolutely. And actually that leads on really nicely to another question we've had, which is probably one for Rosie, which is we're hearing sad tales of relatively new buildings being deemed obsolete due to the amount of effort to redesign services for an alternative use. Are there any good tips to giving buildings a potential better life expectancy?
So I think I'm just continuing what Craig is saying effectively, but a bit more niche on the building services, in that, this building standard of a building lasts 60 years just isn't true, is it, for structure? But in terms of services, actually, those services are more likely to be 20 or 30 years. So, fundamentally, conversation very much upfront with the client, current users, future users. That building has to be flexible. It has to be dynamic. It has to be adaptable. It has to meet what the client wants it to do now. And it has to meet climate change criteria. We have to be thinking of what's going to be happening in our climate in that lifespan. And the other big ones are, burying services in the fabric, burying services under inaccessible ceilings. All of that renders those services totally unadaptable. And actually, services need to be adaptable. The services are very much more dynamic in terms of what's happening in that building at the current time, upgrades to certainly fiber systems, comm systems. So all of those pipes and cables, actually, we'd benefit a lot if they're accessible, and that we're not having to dig into building structure to get back to them. But very much the approach is talking about how can we make that building fit for now, fit for climate change, and fit for future client uses, and how can we access those services that we're putting in now.
Yeah, absolutely. Perhaps a niche question for you, Craig. question from Nick Simpson. We see more and more use of ground screws for smaller buildings. Do you have a view on these, and are they durable in the long term? Do you think they're part of this discussion around embodied carbon?
I think they will definitely save you some carbon in the short term. Our ground screw is going to last a significant period of time. They'll last a significant period of time for us as an individual human being. But are they going to last a long time? No. So sometimes a low carbon solution is a false economy. Don't get us wrong, if in the current climate where we end up knocking down buildings and pulling out foundations and we design for waste and we design in a wasteful way, a ground screw will save, because that building's probably going to get pulled down within 100 years, or someone's going to deem it's not appropriate anymore. And the fact those screws wouldn't be lasting much longer after that isn't the end of the world. But if you've got a building which is truly adaptively designed, there's no more practical way of putting a foundation than mass concrete. Reinforced concrete has the ability to corrode, because you can get corrosion on the roof, but just mass concrete. In a perfect world, you would be in a scenario where you could convince someone somewhere at the RICS that stone foundations are okay, but that's going to take a long time, because concrete's just supposed to be cheap stone, but it's no longer cheap stone. It's expensive stone, and you have to burn limestone to produce the cement to be able to make it. It's like madness. But unfortunately, we live in a world where a lot of, like I said it before, building is a commercial activity. So we live in a world where ultimately decisions are sometimes made by people who shouldn't make the decisions, and they don't really understand what they make the decision on the basis of. But in the short term, the most effective way you can ever put a foundation in the ground is just mass fill concrete, because that will last forever, literally forever. As long as someone doesn't then decide, oh, it doesn't quite fit the layout, or I can't quite justify the loads. We don't know what the original calcs were. There's a lot of that engineers are guilty for, as in like bad design for making bad decisions. But you can't influence that. There's nothing you can really do about that. But as architects, what you can do is think, well, if I'm putting concrete in the ground, can I do it in such a way that it is going to be ultimately reusable? Or do I have a really, really niche layout where I say, oh, well, I need to have this wall there because of X, Y, Z. So because of that, it's really, really, really appropriate for this layout. But if anyone ever tries to use it for anything else again, it just doesn't work. Think about your layout. Are you being too precious about something? Or go the other way and think, well, actually, this is what the client wants and needs, but it's pretty hypocritical to then frame it through the lens of embodied carbon if you're making decisions that are bad decisions in relation to embodied carbon.
Yeah. Fantastic. Good. Well, look, I think we could go on for ages, but I'm very conscious it's almost 9:30, and people have probably got their jobs and their projects to go back to. So, firstly, if we could just thank you both very much for taking some time out this morning and talking to us about collaboration. I think it's been really valuable. I think definitely one of the best sessions we've had so far. So thank you very much. As soon as we have this recording, we'll pop this up on our YouTube channel, and people can share that around. Just before we finish, I just wanted to quickly share the slide for the next session. This is next Wednesday. So next session, we've got tools for smaller practices. So a hybrid event online and at the Farrell Centre, starting at 9:30. So we've got two speakers. First up, we've got Tom Bennett from Studio Bark. Tom's going to be talking about their new sort of lightweight embodied carbon tool for small practices. And we actually have a speaker lined up now for the second part of that. This was about how we used AECB pH ribbon for embodied carbon calculation, and I think that's going to be Daniel Dyer from Mawson Kerr. So as I say, look on the RIBA Eventbrite page for that, and we'll hope to see you next week. Thanks all for coming, and thanks again to our speakers.
Thank you.
Thank you. Thanks.
Brilliant.